After students learn diagonalization, they often ask, well, where is it used? What's the purpose? And we're going to find out in this particular video where we examine solving systems of differential equations. Now, if you look at the first system of differential equations on the left in terms of y sub 1 and y sub 2, and you were going to ask yourself, well, how am I going to solve that system? You might be hard-pressed to do so, especially if you're trying to use separation of variables, because both these equations involve both of these variables together. We call this a coupled system. It's not possible to separate those variables. Whereas on the other side here, with this particular system of differential equations, we just have one variable used in each equation. We could easily separate those variables and solve. So again, the behavior of this first system depends on two variables. So it's going to be a challenge to try to isolate them. But in the second system, each equation only involves one unknown function. In fact, if you think about it, you could just look at that second system and probably solve for the functions u1 and u2 just by looking at it, or as mathematicians say, by inspection. So think, what function when you take its derivative is equal to twice itself? In the second line, what function when you take its derivative is equal to negative 3 times itself? Well, no doubt you remember in your Calculus 1 class what function has a derivative that involves itself. Of course, we're talking about the exponential function e to the x, or e to the whatever. So in this particular case, we could also represent that second system in matrix form, and you would have a column vector on the left in terms of the derivatives, u1 prime, u2 prime. You have a nice coefficient matrix that's a diagonal matrix, which would give you this particular system, namely u1 prime equals 2u1 and u2 prime equals negative 3u2. And as we suspected, the u vector, that is the values of u1 and u2 taken as a column vector together, is simply some multiple of e to the 2x and some multiple of e to the negative 3x. You could easily do a quick check. What's the derivative of c1 e to the 2x? Well, that would be, let's think, c1 times 2 e to the 2x, or 2 times c1 e to the 2x, again, twice the original, and you get similar outcomes here with the second component of u vector. Again, what does this have to do with solving systems of differential equations? So what we're about to do, you're going to see that we're going to exploit the fact that having a system of differential equations with a diagonal matrix as its coefficient matrix, this is very easy to solve. We're going to exploit that fact and try to create circumstances with coupled differential equation or coupled systems so that we could perhaps make this diagonal matrix occur. And of course, this makes us think of the diagonalization techniques that we learned about earlier. So let's go back to that diagonal system that we had expressed in matrix form. Okay? Is it possible to somehow relate this to the previous system we had before? That is, given a constant coefficient first order homogeneous linear system, which is just a long-winded way of saying given a system y prime, y vector prime equals some coefficient matrix A times y vector, whose coefficient matrix A is not diagonal in and of itself, but is diagonalizable. What if a coefficient matrix is diagonalizable? Could we somehow make this happen where we could easily solve for the solution by inspection? Right? Can this fact be used to reveal what the solution's y vector will be? Well, it's all predicated on whether or not, again, matrix A is diagonalizable. So if matrix P is an invertible matrix that actually diagonalizes matrix A, such that y equals p times u vector for some unknown vector u vector, then this means we could solve another linear system in terms of u, whose coefficient matrix is diagonal. Now that's what the textbooks say, but what does it actually mean? Why is this possible? Well, if you think about it, both the components of y vector and the components of u vector are from the same space. They're in two space. So we know the column vectors of matrix P, which diagonalize matrix A. We already know from our previous studies of diagonalization that the column vectors of matrix P are made up of the linearly independent eigenvectors from whatever particular eigenvector family that we're dealing with. And we know that those eigenvectors that make up those columns are linearly independent. So they can span R2. They can span whatever space we're dealing with. So certainly the solutions for y vector in the original system of differential equations can be simply expressed as some linear combo of the eigenvector columns that make up matrix P, because we know that those columns span the space we're talking about. So here's the usual development that helps us appreciate what we're going to do in a moment. So once we realize that we can express the solutions y vector to the original differential equation system by taking the transformation matrix, if you will, P, which is made up of column vectors whose columns are eigenvectors from particular eigenvector families. Then we can do a little progression that will show us that it reveals that it really boils down to a diagonal matrix system. For example, if we go through this process, now take the derivative of both sides. You'll have y vector prime equals p u vector prime, right? We don't touch the matrix P. We just take the derivative of the column vectors y prime and u prime. And of course, since P is made up of column vectors that are linearly independent, we know it has an inverse. So we pre-multiply both sides by P inverse. And that gives us this step. P inverse y prime equals u prime. But now recall, y prime equals ay. Well, that was the original system that we're trying to analyze. Okay, so if we recall that and substitute, wherever we see y prime, substitute a times y in its place, we now have this step. Okay, so that's where we're at. P inverse a times y equals u prime. And now recall, this was all predicated on the fact that we can express the solutions y equals p times u, right? We could just transform to get the solutions to the original differential equation system, y. We just transform using matrix P times u. And if we do that, we make a substitution. That is, here we have y, and now we're going to substitute y equals p times u. So now we have a familiar face. P inverse AP, which is a very familiar structure that you studied when we looked at diagonalization. P inverse AP times u equals u prime. Wait a second. P inverse AP, we know that P diagonalizes A. So that is the diagonal matrix we seek. So another way of writing this step right here, P inverse AP u equals u prime, is simply u prime equals the diagonal matrix D, which we'll call P inverse AP. U prime equals diagonal matrix D times u. So again, starting was all predicated on the fact that y equals some matrix P times u, where P is made up of, the columns of P are made up of linearly independent eigenvectors. And that leads us logically to this system, u prime equals diagonal matrix times u. Okay, with all that development, where's the easy part come in? Well, remember, this was the easy part. We can solve systems of differential equations with a diagonal matrix by inspection. So keeping that in mind, we're now going to solve this system for u by inspection, and then we'll just take our result, multiply it by matrix P, and we'll have the solutions to the original differential equation system. So let's go back to that original system. In fact, here's the original coupled differential equation system I had earlier, and I'm even going to throw in some initial conditions. Let's go all out here and solve for everything we possibly can. What if I told you that y10 equals 1 and y20 equals 6? Can we then solve for the solution to this system? Well, first we need to find the eigenvalues of the coefficient matrix A. We need to know if A is diagonalizable, because if it's not, this won't work. So familiar technique with the characteristic equation, we take A minus lambda I and we solve for our lambdas. You've gone through details like this in the past, no problem. And using factoring techniques, we show that one eigenvalue is equal to 2 and the other eigenvalue is equal to -3, which leads to the question, how can we tell at this stage that matrix A is diagonalizable? Do you recall? Well, hopefully you realize that since you have two distinct eigenvalues for this 2 by 2 matrix, we know, we're guaranteed that this matrix is diagonalizable. So we're quite confident that we could use this technique that we just demonstrated theoretically to make a very difficult system of differential equations turn into something very simple. So again, now we want to find the bases for the eigenspaces, so we can just take a member from that family and make the columns for matrix P. Remember, the columns of matrix P are linearly independent eigenvectors from each eigenvector family. If you put each eigenvalue into this system, substituting the lambdas, you will find your eigenvector families. So the first one is an easy thing to take the reduced row echelon form of to get this structure. So we have that the first eigenvector family is simply a multiple of 1, 1. And if you substitute lambda 2 equals negative 3, you would get that the second eigenvector family can be expressed as a multiple of 1, negative 4. You could have also expressed it as a multiple of negative 1, 4th 1. But any way of expressing eigenvector families that maintain the ratio that's appropriate would be fine. So I chose to express it as a multiple of 1, negative 4 for the second eigenvector family. Okay, now that we got the two eigenvector families, well, we need to pick a member from each family to make up the columns of matrix P, the transformation matrix. Most people just let the parameters in front be 1, and you just take those actual vectors that you see in front of you. So we're going to make matrix P by augmenting 1, 1 with 1, negative 4. Important questions to keep in mind. Why are those columns linearly independent? Well, if you look at them, you can clearly see that neither of them are multiples of one another. So clearly those two are linearly independent, as they should be, since they come from different eigenvector families. And now here comes the fun part. We want to evaluate P inverse AP to get that diagonal matrix, which will unlock this puzzle for us. So P inverse AP, you take the inverse of matrix P that we just constructed. You take the original coefficient matrix A from the original differential equation system, multiply it again by matrix P on the right, and lo and behold, we have another familiar face. We have a diagonal matrix with those same numbers we talked about in the second system on the first slide, 2, 0, 0, negative 3. So what this means is that we were able to create this system, U prime equals du, right? It is a diagonal system, if you will. The coefficient matrix in this system is a diagonal matrix. And as we said earlier, that means that the solution vector to this simpler system is simply a multiple of e to the 2x, another multiple of e to negative 3x. We could solve that just by looking at it. But the beautiful part is we can now use that to make our solutions to the coupled system, which we were having difficulty with earlier. Remember the relationship. The matrix P is a transformation matrix, if you will. It's going to transform the solutions from the diagonal system that had U vector. It's going to transform it to give us the solutions to the coupled system, which was the Y vector solutions that we seek. All we need to do is multiply the column vector solution U times matrix P, which was made up of those linearly independent eigenvectors. And lo and behold, we have a general form of the solution for the original system. It's that simple. And of course, with that general form, you could finally use your initial conditions. Let's see, what were they again? We were told that y sub 1 of 0 equals 1, and y sub 2 of 0 equals 6. And if you plug those in, you get another linear system, this time in terms of C1 and C2, so more linear algebra to the rescue. If you just reduce row echelon form that system after putting it in an augmented matrix, you find that the two constants are C1 equals 2 and C2 equals negative 1, leading to the solution to this system. Again, powerful technique, all based upon whether or not the coefficient matrix in the original coupled system was diagonalizable. If it is, we have a neat way of avoiding all the difficulties in solving systems like that. So let's recap. Why do we learn about diagonalization? Indeed, why do we learn about eigenvectors in the first place? Well, they make it very easy in situations like this to solve for the solution to differential equation systems. I want you to take a look back, which is often a very important thing to do in mathematics. Look back at what we just did. Look at the solution to y vector, Look at the solution y vector to that first coupled system. It's y1, y2 equals, okay, so we had the matrix P times the solution U, and we got this. But isn't it true when you look at this result, you can see, quite naturally, the eigenvectors embedded in this answer. Really, what we're taking is c1 e to the 2x times the first eigenvector to give us this piece, and c2 e to the negative 3x times the second eigenvector to give us this piece. So that leads to the following theorem, which tells us that basically to express solutions to systems of differential equations in which the coefficient matrix is diagonalizable, all you need to do is take linear combinations of the eigenvectors that you see here. So this theorem says if the coefficient matrix A of the system y prime equals AY is diagonalizable, then the general solution of that system can be expressed simply by taking c1 e to the lambda 1x times the first eigenvector plus c2 e to the lambda 2x times the second eigenvector all the way to the end until you run out of eigenvectors. So the reason we learn about eigenvalues and eigenvectors is because eigenvectors make wonderful basis vectors for the solutions to systems of differential equations. And that's a key takeaway. Please remember that. Eigenvectors make good basis vectors for solutions to a linear system of differential equations. So I hope you enjoyed this video, and look out for the next Pronotes video coming up soon.